Hi, my name is Sam Bourgault, and I'm presenting our paper, CoilCAM, Enabling Parametric Design for Clay 3D Printing through an Action-Oriented Toolpath Programming System on behalf of my three co-authors, Pilar, Wiley, Avi Farber, and Jennifer Jacobs. Hand coiling is the ancient practice of building vessels layer by layer with hand-rolled coils. Ceramicists using this technique can build vessels showing a wide range of aesthetic and functional qualities. Similar to coiling, clay 3D printers fabricate 3D structures by extruding coils of clay, which are vertically layered and compacted in succession. While clay 3D printers use similar materials and concepts as hand coiling, they require fundamentally different tools. Clay 3D printing often involves a workflow that is similar to other forms of digital fabrication, wherein craft people develop a geometry and computer-aided design, CAD software, and convert the geometry into machine instructions using computer-aided manufacturing, CAM software. Circumventing CAD and designing exclusively in CAM offers unique opportunities for clay 3D printing. In a CAM-based design workflow, the designer defines the artifact geometry by specifying toolpath operations to be executed by the CNC machine rather than by automatically slicing a solid digital model. We therefore observed parallels between CAM-based design and hand coiling techniques. In both cases, form emerges from the interaction between each action enacted by the craft person or machine and the material response. We use the term action-oriented to characterize manual and machine fabrication workflows in which form is conceived of through iterative manual or machine actions. HCI researchers have developed methods to generate 3D toolpaths and control thermoplastic 3D printing parameters. But while CAM-based design for additive fabrication has primarily focused on thermoplastic printing, we seek to extend these approaches to clay. Digital fabrication practitioners have also used CAM-based design practices to develop products with design elements that result from the interaction of specific machining behaviors and the property of various materials. Since clay 3D printing was first introduced in 2009 by the Unfold Design Studio, many contemporary artists and designers who use that technology rely extensively on creating works by programming toolpaths in CAM general-purpose programming languages. Sarah Rosanna Brady makes speculative sculptures examining tension between indigenous craft and space colonialism. Timea Tiani uses material-specific techniques to fabricate textile-like ceramic objects, and Foran and Suan create intricate 3D printed pottery home goods. Out of the 9 prolific practitioners using clay 3D printers that we looked at in our paper, we found that at least 6, including Brady, Tiani, Foran, and Suan, use CAM-based design. These practitioners shows how CAM-based programming is already common in clay 3D printing craft. Drawing from our analysis of manual and digital ceramics fabrication, we theorized that an action-oriented approach for clay 3D printed could allow creators to design digital fabrication toolpaths that reflect clay material properties. To investigate this theory, we developed CoilCAM, a visual coding system that enables the programming of mathematically defined toolpaths to create 3D printed ceramics. We developed the CoilCAM system as part of a craft research residency aimed at informing the design of new computational fabrication technologies through collaboration with craft experts. We invited 2 professional ceramic artists, Pilar, Wiley, and Avi Farber, who are also authors on this paper, to collaborate in our research lab at the University of California, Santa Barbara for 3 months. We used a collaborative process where we combine systems design and prototyping with the production of finished ceramic artifacts by professional craft people. For more details about the different phases of our residency, please see our paper. During this residency, we developed CoilCAM. We implemented the system with the general-purpose visual programming language Grasshopper, but where existing Grasshopper components generate and modify solid geometries, we developed a set of primitives using custom Python script components that generate machine toolpaths suitable for clay 3D printing. In the remainder of this presentation, for clarity, we present CoilCAM programs as a series of diagrams with color-coded nodes that correspond to our custom Grasshopper components. Programming in CoilCAM is structured around procedural transformation of a cylindrical toolpath, represented by the toolpath unit generator component. This component has 4 shaping parameters: radius, scale, translate, and rotate, which can be modified to create different forms and textures. The radius shaping parameter can create waves in the radial geometry of a layer, for instance. The scale shaping parameter can scale up successive layers to create a flared opening. The translate shaping parameter can shift layers through translation to create a tilting form. And the rotate shaping parameter can iteratively rotate each layer to create a twisted form. To modify these shaping parameters, we use a set of function operators that can be chained together to create increasingly complex functions. The system also implements 2 Boolean operators, union and difference, which enable Boolean operation to happen at the level of the toolpath, ensuring the resulting designs are feasible for fabrication. By using the CoilCAM primitives in combination, we can apply rapid variation and complexify a design quickly. I will walk you through the making of the texture cup presented in figure 11 of our paper. We first start with a linear function operator on the scale parameter of the toolpath unit generator. This creates a flared cup shape. To create protrusion on the surface of the cup, we added a square function operator on the radius shaping parameter of the toolpath unit generator. We then use a staircase function operator on the rotation shaping parameter to offset the protrusion around the surface. Finally, to create a gradient in texture, we linked a sine function operator to the square function operator on the radius shaping parameter. This example shows how CoilCAM supports rapid iteration to create forms and textures. CoilCAM is also suitable for creating functional clay artifacts that blend hand-shaped and digitally fabricated qualities. For example, we created a tea set that is both watertight and capable of pouring, and that shows parametric variation and the creation of non-cylindrical forms. To evaluate our system, we reinterpreted signature artworks from Avi and Pilar and used these artifacts as a foundation for a discussion between the 4 authors of this paper. For instance, we recreated Avi's end-built flask and Pilar's 2-headed vessel. We share more details about this process in our paper. To identify opportunities for future development, we conducted a 2-hour conversation between the 4 authors of this paper about the resulting artifacts of our evaluation. The discussion enabled us to identify how CoilCAM's design feature can support aspect of action-oriented workflow. First, as a parameterizable visual programming node system, CoilCAM provides craft people to work through systematic and emergent variation, which aligns with how manual fabrication offers rapid ways to establish and refine a form. For Avi, for example, having the possibility to use simple operation and get so many different shapes was appealing, as it could drastically change the feel of the puck. Second, CoilCAM's continuous and discrete function operators enabled the design of both form and surface texture that support material expressiveness. Third, CoilCAM's representation of machine actions enabled craft people to plan for manual modifications, such as part assembly of 3D printed clay artifacts. Pilar remarked that by manually forming a printed handle, you can engage with the 3D printed lines in this really cool way and really use the best of this material in the process. Fourth, the low-level control CoilCAM provided over toolpath operations enables skilled craft people to plan for collaborative opportunities with the 3D printer and clay during fabrication. Finally, these design features demonstrate how CoilCAM-based design strategy can support aspects of both manual and digital action-oriented workflows. More broadly, the result of our work provide support for viewing digital fabrication workflows as a form of craftsmanship and show how skilled manual production and digital fabrication are complementary rather than opposing factors. CoilCAM directly contradicts the personal fabrication model that situates digital fabrication users as consumers and circumvents skill development. Rather than only focusing on consumer-oriented model to grow fabrication applications, we argue that the field of skilled manual digital fabrication is a critical focal point for future HEI fabrication systems research. To pursue this direction, our model of action-oriented workflow can serve as a useful example in emphasizing system representations that reveal the design actions of humans and machines and create opportunities for fruitful interactions between the two. Thank you to all my co-authors, Pilar Wiley, Avi Farber, and Jennifer Jacobs. For more details on CoilCAM, please see our paper.